Welcome everyone to today's ECR seminar, and our speaker today is Sylvia Ploeckinger. She did her PhD at the University of Vienna, and after that she did postdocs in Leiden and Durham, and she will return to her alma mater later this year. So please go ahead, Sylvia, with your talk. Oh, and
thank you very much. So let me quickly share my screen. I assume if I don't hear anything otherwise that everything works fine. Thanks, Christoph. So yeah, thanks for the invitation. Thanks for having me. And yeah, I will today talk about, well, the title of my talk is Can Cosmological Simulations of Multiphase Galaxies with Different Dark Matter Models Solve the Small-Scale Problems of LCDM? And I already want to spoiler that right from the start and say that this throughout the course of this talk, I will answer this question with a very confident maybe, as it is so often the case. And so this is all still work in progress, but we hope that with the projects that I'm involved in, that we will make a big step towards a better understanding of these processes. So this is something that, of course, this work has not been done in isolation. I have a lot of colleagues that I work together with. They are mostly from the University of Durham in the UK and from the University of Leiden in the Netherlands. I want to highlight a student of mine, Stefan van der Giessen, and whose results from his thesis I will also present towards the end of this talk. So let me set up everything by giving a little bit, very, very briefly, of historical context when the field of cosmological simulations was a little bit easier to digest still. So you can see on the right here an illustration of the Millennium simulation. So at that point, this was a pure n-body simulation. So that means that all the mass in the universe was just described by dark matter, meaning that it only interacts gravitationally. And these simulations were a really, really powerful tool and still are to test cosmological models. And the nice thing about that is that they have very simple ingredients. So basically, if you go to co-moving coordinates, where the expansion of the universe is then kind of taken out, it has very, very simple equations. That does not make these simulations necessarily simple to run because there are a lot of technical details that you need to worry about of running these simulations with billions of particles. But the equations for just the interaction of the particles, if it's just gravitational, are very, very simple. So it is a very well-defined physical model, and then you can compare the results that you have to observations, for example, to very large-scale surveys, and you can. And this was the big success of the LCDM model, the current standard cosmological model, that this seems to work very well on large scales. So very, very simple model, and with a great power in comparing some aspects between the simulations and the observations. But what about small scales? So if we think about small scales now in a cosmological context, we talk about scales of individual galaxies, more massive galaxies, but also then down to dwarf galaxies. So there, it's a bit, everything gets a little bit messier, everything gets a little bit trickier, because when you set up those simulations and you are testing them, you want to test some theories. What you're testing is not just the cosmological model anymore, as you used to do before. You can assume your dark matter particle, your other ingredients in terms of the composition of the universe, and you can just run that and compare that, and you only test your cosmological model. Now, with the more complex simulations that we have nowadays, you don't only test the theories, different theories of cosmology, but this is kind of intertwined with different theories of galaxy formation, then a lot of numerical issues, a lot of subgrid models, because of course you don't have infinite resolution, so you need to make a lot of assumptions about the processes on scale that you do not resolve. So the problem is now that if we now compare simulations with observations, and there is a mismatch between the two of those, then it is sometimes difficult to disentangle what is the component most to blame for any given mismatch. So is it something in the cosmological model that we don't fully understand, maybe different forms of dark matter? Is it something more in the galaxy formation aspect? What I mean with that is anything that is resolved, like all the gas dynamics. Is it something that is mainly related to just some numerical issues, just how things are implemented in the code and how things are actually simulated rather than the real physical process behind that, or how the subgrid models are implemented? And then, of course, another component is that oftentimes when you compare simulations to observations, it's difficult to compare the same things. In simulation, the basic information that you have about your different components is, for example, the mass distribution. But while for observations, you usually get a specific light, for example, from a very specific component. So this be it stellar light from a very specific line emission, or you get emission from a very distinct gas component, specific gas properties, be it neutral hydrogen or molecular gas in the form of CO. So to compare those things exactly is tricky in itself. So if there is a mismatch between observations and simulations, you also need to have a very close look on what you're actually comparing, whether your comparison is adequate for what you're looking at. So now it's a lot more messy than when we just had the n-body simulations with the very simple gravitational equations. So with that in mind, I would like to just remind you of some of the small scale problems of the current cosmological model. So these are things where you would refer to as there has been a mismatch traditionally between observations and simulations. So they are all quite established and kind of old at the moment already. But I will like to give like a modern twist on each of them and bring them back into the current time. So the missing satellites problem. So this would be that in dark matter only simulations, you have a lot more satellites than what we observe. This is commonly agreed to that this has been solved. And this has been solved by different components. So first of all, we can't just compare dark matter only simulations to dwarf galaxies, because not every dark matter halo will form a dwarf galaxy. So we need to, what was needed was to improve on that to really compare like for like. And then there was also, for example, in terms of galaxy formation, it turned out that the epoch of reionization has been very important to shut off star formation in very low mass halos. And once this is included in the simulations, then the number of luminous dwarf galaxies, satellite galaxies, is reduced drastically, and then it matches with observations better. So this is something that is kind of widely regarded as being solved. The reason why I still have it in my talk today is that I think that this will become very interesting again in the next few years, because we have established now that that for the scales of kind of the classical dwarf galaxies, or the dwarf galaxies around the Milky Way that have been detected by the Sloan Digital Sky Survey. But in the next few years, there will be a lot of big observation campaigns coming, which focus on the low surface brightness universe. And so that means that we will get a lot more data on ultra-faint dwarf galaxies. What I'm showing here is on the x-axis, we see the stellar mass of dwarf galaxies. And on the y-axis, their absolute magnitude in the R band. And this band in here with the extrapolation to lower masses shows roughly where the known dwarf galaxies are located in this band. And then the horizontal lines indicate the completeness limits for different surveys. So the lowest one is the current state of the art is the DSS survey. But in the next few years with the Vera Rubin Observatory, this will be pushed to a lot fainter galaxies. So that means that in the deep drilling fields of the Vera Rubin Observatory, within a distance of about 4 megaparsecs, this means within the local group, we will be able to detect ultra-faint dwarf galaxies down to stellar masses of roughly 100, of maybe a few hundred solar masses. And we will even detect ultra-faint dwarf galaxies out to cosmological distances. So this would be the completeness limit for a distance of 45 megaparsec. And we will also learn a lot more about general dwarf galaxies at very large distances. So that means this is currently a regime in terms of dwarf galaxies masses that is not very well explored at the moment, but where we would expect differences, for example, in terms of different dark matter models. So given whether these exist or not, can potentially rule out different dark matter models. So this relates back then to the cosmology aspect. The second one of the small scale issues that I have listed here is the traditional Cusp core problem. Again, this is so just a quick reminder that this, if we focus on the data points now, for now, I will come back to explain the rest of the lines in a moment. We can see that some observations of some galaxies have very steeply rising rotation curves. So that would refer to a central cusp in the dark matter halo, while others have very slowly rising rotation curves. So this would be more applicable or for a dark matter core. So for a constant density in the center of this galaxy. The thing is that this has also been regarded as being solved, and this aspect has been solved or has been claimed to be solved by just this aspect of choosing different subgrid models or numerical issues. For example, a collaborator of mine, Alejandro Benitez-Chambay, has shown that that just by varying some parameter of which density you allow stars to form in a simulation can make your dwarf galaxies either have a central cusp or have a central core. So this then has nothing so much to do with the physical issues at play, but this is just something that numerically is defined. So if you choose a given star formation density threshold, then you might end up with either cusps or either cores in dwarf galaxies. Why I now think that this is still something that we need to have an eye on and that I don't think is completely solved yet is that in 2015, Kyle Oman gave that a modern twist by saying that it's not so much a cusp core problem, because with different numerical prescription, we can form either a cusp or a core, but it is more a rotation curve diversity problem, meaning that while we can make simulations, we can set them up in a way that they produce either cusps or cores, it is very difficult for them to, within the same simulation, get both of them. So coming back to this figure that I had showed before, these are observations of two dwarf galaxies with the same very similar masses, so the same maximum velocity, as you can see here, if you compare where they peak, where their maximum rotational velocity is. But they have very, very different profiles based on the rotation curve. And then the lines here are from simulations, from either dark matter only or from dark matter and hydrogen simulations. And you can see that in this case, the simulations predict a central cusp, but they do that for all their galaxies. So other simulations might have cores for this, might produce cores for this mass range, but as I said before, it's very difficult to get a simulation that does both. So that's why I think just focusing on the numerical issues is not directly solving this problem. In addition to that, there has also been later something shown that it might not only be the comparison with observations, but also the observational techniques that I added here as an additional circle in this complex problem of comparing simulations to observations that can add to this problem. For example, in 2019, Kyle Oman has shown that when you take a simulated galaxy and you put it at a specific inclination, so an inclination that makes it easy to derive rotation curves, but then you rotate it azimuthally, and you construct rotation curves in two different directions. So for example, here the blue line would be one direction and the red line would be the other direction. Then you can get, for the same galaxy and for the same inclination, you can get either a slowly rising rotation curve, so this would correspond to this one here, or a steeply rising rotation curve. So that means that it's not even yet fully settled if the observations have this diversity, or whether this is something that could be maybe improved with different modeling. And potentially also that the simulations that were used here to show this problem might also overstate this problem, because they use only a single phase medium for their interstellar medium, which might have made this different modes worse than they actually are in reality. So we've had that, and the third problem, the too big to fail, I will only mention now very briefly, because it can be solved with the same idea of just lowering the dark matter density in the center of galaxies, so it kind of is connected to the previous one. So now this is the picture that we have, this complex picture of making sure that the simulations are giving us what we think they do, how to address differences between simulations and observations, and all the complexity that comes with that. So what is now the way forward from this? And my approach to that is, and that of the team I'm involved in, the teams that I'm involved in, is that we just do the best we can on all these different fronts, and then see which most kind of minimizes the disagreements with the observations. Because all these issues that I have just presented, all these small scale problems of LCDM have all been proposed to be solved by all of these components. So for example, using a different form of dark matter, so which would fall into the cosmology category, or modeling different things better, or improving the resolution of the simulations to model the dwarf galaxies better, for example. So now the kind of second half of my talk will cover what we in the teams that I'm involved in, what we are doing to improve upon all these issues in the forthcoming simulation projects. So starting with the category of numerical issues and subgrid models, a very quick update on what is the current state of the art. So there is a really nice review by Vogelsberg et al. In 2020, where they, here in this nice illustration, show some of the state-of-the-art simulation projects, and these are only the ones that simulate full cosmological volumes until a redshift of 0, so until today. There are other projects that focus on individual galaxies, like zoom-in simulations, so I'm not talking about these today, only about the ones that model full cosmological boxes. So these simulations, so here are some examples of individual galaxies from the Eagle simulations. They look realistic, like real galaxies, so they don't form just dense clumps anymore, as they did in the very early simulations when feedback was not implemented properly. So there has been a lot of improvement in the last few decades on that. But still, all of the simulation projects that I mentioned here model the interstellar medium as a single phase. So if you would take all your resolution elements and you would put them in a phase space diagram like this, where you have on the x-axis, you have the gas density, and on the y-axis, you have the gas temperature, then it will look, for example, for Eagle, it will look roughly like this. And note that there is no cold gas here. So there is no gas below 10 to the 4 Kelvin and with densities above 0.1 particles per cubic centimeter, because this gas is modeled by a so-called effective equation of state. And sometimes this is also called the Springer and Turnquist 2003 model, which has a slightly different shape, but overall it all means that there is no cold gas modeled explicitly in the simulations. But this is all kind of all the processes that are not resolved are swallowed by this effective equation of state. So this has always been argued that this is necessary to prevent spurious fragmentation for simulations with this kind of mass resolution of 10 to the 6 solar masses. We are currently questioning that, so I have a paper in preparation about that in detail on how you can still, even for a lower resolution, how you could get away without using this effective equation of state, because of course, all the interest, or a lot of, not all the interesting stuff, but a lot of interesting stuff happens in this area of cold gas and high density. So star formation obviously happens here, even though we will not be able to really resolve the collapse of giant molecular clouds in cosmological simulations anytime soon, but we could still do better in modeling the cold gas phase. And there is a lot of observations would target this gas. So they would target, for example, neutral hydrogen, the H1 line, or CO, which is all here, which is all not modeled directly. But this is the current state of the art. So what we want to do now, so this goes in the line of this category of improving on the numerical issues, and to say we want to have a better comparison with observations. We want to compare like for like, and if we compare with H1 rotation curves, we want to really know where is our H1 and how it is moving and how it is behaving kinematically. So with the new model that we are doing is that we don't have this equation of state or this pressure temperature floor, but we now have all the different gas phases. So we have, for example, now here the warm neutral medium, we have the cold neutral medium, and then we also have the area where molecules form. Of course, we don't get the full tail to the highest densities in this simulations, but still we have all the gas phases, all the important gas phases present. You also can see here like a narrow stripe in temperature. So this would be the H2 regions around very young stars that are forming, that are ionizing the gas around them. So there's a lot of more information in here. And then also it improves your resolution, because imagine even if you have infinite mass and spatial resolution, if you still have this equation of state, everything will still be smeared out because you have this artificial pressure term that keeps your gas very smooth. So here on the left, this would be with exactly the same mass resolution. You would have a galaxy with this equation of state, and on the right you have it without, and you can see that then there is much higher density contrasts here on the right. So you gain resolution without adding more particles. And this is this multi-phase ISM, or modeling the cold gas phase, is very important for all these aspects. So first of all, as before, to compare like for like with observations. But also because in very low mass dwarf galaxies, this artificial pressure floor can impact how stable they are against, for example, stellar feedback and so on. So if you don't allow your gas to cool down, but you always keep it kind of diffuse and warm, then any feedback event you have might evaporate at a lot faster than you would otherwise. So for dwarf galaxies, and especially then when you're entering this regime of ultra-faint dwarf galaxies. This can have an impact whether you see your galaxies, whether they exist in your simulations or they don't. So this is something very important to include. Of course, we can't just drop this pressure floor and not care about what is going on, because there is a lot of things going on in the cold gas phase that could easily be ignored before. So we have molecules that form, dust is very important. We have shielding from local radiation, also from the general UV background. We have stellar winds that form. We have H2 regions that were already visible in the phase space diagram that I have showed before. And we also have radiation pressure. So these are a lot of processes that we now have to include that could be safely ignored before if you keep your effective temperature at above 10 to the 4 Kelvin. So now just a very brief overview on the simulations that I'm presenting now. So these were run with a new hydrodynamic code, which is called Swift, which has been developed to make the best use of modern architecture. So to be able really to run efficiently on thousands of cores for very large scale simulation projects. It uses a new, so it is an SPH code. It uses a new hydrosolver, which was recently published by Josh Borrow. All the cold gas physics that I have been shown before, to include like molecules and dust and so on. So this is all pre-tabulated. And this is published in Ploeckinger and Shade 2020. I'm also writing up how we are doing the early feedback. So this means the stellar winds and the H2 regions and radiation pressure. There have been some updates from Eagle in how the supernova energy is distributed. And then also all the analysis has been done with a software package that's called Swift SimIO, which helps to analyze the Swift data. So this is a large simulation project. The flagship run, unfortunately, is not done yet, but we already have the first papers are coming out slowly, and we expect the flagship runs to be done later this year, and then there will be a large amount of data that we will analyze in great detail, and I'm really excited for that to happen. So far we are still putting out the method papers. Some are already out, as I mentioned here, and many, many more are in preparation. So now the advantage, as I had said before, is the big step forward is that we now have a multi-phase interstellar medium. So that means we not only have the total gas with much finer and higher density contrasts, but we also have it split now into its different components. So for example, we can say where is our atomic neutral hydrogen, where is our molecular hydrogen, and then because this is not done in post-processing as it can be done otherwise, if you have a single phase to look to distinguish the phases after the simulation is run. So this is now done on the fly, basically. And because we don't have this pressure floor, we also get very nice and thin disks of our galaxies, because in the current simulations, this artificial pressure floor stabilizes the disk vertically against collapse. And that means that disks, for example, in Eagle, but also in all the other simulations, are too puffy. So they are not thin enough, which again then makes it more difficult to compare with observations, because you have more, for example, of non-circular motions than you would have in observations. So here are some examples from a box. So this is now just at Eagle resolution, so still relatively low resolution compared to what we've had before. But this is one of our test boxes where we can see the stars face on and edge on, and then the H1 face on and edge on, and also then the molecular hydrogen face on and edge on. So just some examples just to illustrate what is going on. As I said, this is relatively low resolution, and still we don't need this pressure floor, which is very nice. So we get this phase decomposition even already for relatively low resolution, while the the high resolution boxes that we are planning to do should have almost 2 orders of magnitude lower mass per particle. And then we can now also, if we analyze the data and we look at, for example, the kinematics, we can then also get closer to what observations would do and get the velocities that are weighted by the different components. So this is a very simple model, right? This is just for illustration. This is just mass weighted. But of course, we now have the different components, so we can decompose that nicely. As I said before, so this is only mass weighted, or in the case of the stars, it's luminosity weighted, but without taking attenuation into account. There is a way to really create mock observations. So we have part of what we have published in the tables from 2020 is a long list of different line emissions that we run with the spectral synthesis code Cloudy. And if you want to see an example on how this can be used for mock observations, in this case, it's for C2. Then I would refer you to this paper from 2021 from a PhD student from Groningen, and for more details on that. So now I've covered kind of what we want to improve on the numerical issues and subgrid models side of this whole problem. So to really push for a new multi-phase prescription for the interstellar medium, because we think that this is where we can make the largest strides. And this is one of a very big component on what was currently missing with a lot of the state-of-the-art simulations. And now we move on to another component, which is the cosmology component. So in general, a lot of these large-scale simulation projects because it is the standard model, use the LCDM cosmology, so with cold dark matter. But then on dwarf galaxy scales, we know that these scales are quite sensitive also to which dark matter, which particle is assumed to be the dark matter particle. And so just a selection of dark matter particle candidates. So we can have, for example, axions, we can have fuzzy dark matter, we can have sterile neutrinos, for example. Then there is all different forms of self-interacting dark matter. And all these different types of dark matter will leave their imprint in the galaxies that we observe today, and then also in the simulations if they're implemented with different cosmologies in mind. So to kind of address this issue of some mismatch between observations and simulations on small scales from all sides, there are some spin-off projects which will run the same simulations with the same initial conditions, but adjusted for the different dark matter types. With the full multi-phase medium and all the other improvements that have been made for the flagship project, we will run them also. We are running them already with also with warm dark matter. So in this case, we assume a sterile neutrino of about 7 keV to be the dark matter particle. So this is a project that I'm currently leading, that I got funding from the Dutch Science Foundation, and then there is another project led by Camilla Correa from the University of Amsterdam, which is looking at self-interacting dark matter, that I'm also involved in. So to really make sure that we look at this from different sides. Now focusing a little bit on sterile neutrino, just a quick overview that this model has become popular since the discovery of the neutrino mass. And the idea is, so sterile neutrinos are still hypothetical particles, so they have not been shown, but they would be a very elegant and minimal extension to the standard model of particle physics, because a lot of fermions are known to have both left and right chirality, and neutrinos so far have only shown with left-handed chirality, so it would be an elegant extension to just have also neutrinos with right chirality. And it would also solve some other problems. So it's not only the problem of dark matter, but there are also some particle physics issues that would fall nicely in place if this particle would exist. So for a review, I would refer you to my collaborator Alexei Boyarsky on this, which is mentioned in the bottom of the slide. So what is now the expected difference? If we look at, if we make dark matter warmer and warmer, so that the solid line here would be cold dark matter, where we have scales, so where we have structures on basically all scales, while if we have warm dark matter, then the power will be cut off at a characteristic wavelength or mass of halo mass. So say you would not have halos then, or very few halos below a halo mass of, in this case, for this model, of 10 to the 8 solar masses. So this is just in general. And then you would expect differences maybe on dwarf galaxy abundances, especially ultra-faint dwarf galaxies then. As I mentioned, that this will be something that will be very interesting with the Vera-Rubin Observatory, potentially on the dark matter density profiles, but then also all the empty halos and lack thereof will be interesting for lensing measures. Then, for example, stellar streams and gaps in stellar streams can help to determine whether they have been hit by these empty halos that would exist in cold dark matter, but less so in warm dark matter models, for example, and then also in the circumgalactic medium. So for the sterile neutrinos, this specific form of warm dark matter, we have kind of this behavior. So this would be the number of halos with masses above the mass that is on the x-axis, and this is for one of the simulations that I've done. So this is for a specific volume, and you can see here that this becomes flat just above 10 to the 8. So you have already fewer dark matter halos, say at 10 to the 9, but then below 10 to the 8, they are non-existent. So this means that while the large scale structure is conserved, so this top would be cold dark matter, bottom would be sterile neutrino dark matter. So it's with just by eye, it's basically impossible to find a difference in the first image here in the first panels. But then as you zoom in, then you can see that in the cold dark matter that you have a lot of very small low mass halos in the cold dark matter universe, but you don't have them in the warm dark matter universe. And this again comes back to all the issues that I've showed before. So this might also affect all these issues to different extents. So what I'm showing now is something that I've done with my master student, Stefan van der Giessen. He used the code treefrog to cross-correlate halos in these two simulation boxes. So these would be the ones that kind of are present in both the cold dark matter and the sterile neutrino dark matter box. So this is cross-correlated because they have the same initial conditions beside the smallest scales washed out. So you can just by particle IDs, you can cross-correlate which halos in which galaxy would refer to another halo. And then you can get to a sample that is very clean because you also have some artificial collapses in the warm dark matter. This is just purely numerical, but if you cross-correlate them, then you get a very clean sample that are almost the same number, or that almost follow the same distribution in both the cold dark matter and warm dark matter. So this would be the green and the red line here. And now we can do a two-sample Kolmogorov-Smirnov test. So this is a test that shows you how likely it is that two galaxy populations are drawn from the same parent distribution. So meaning if your p-value is above 0.05, then it is very likely that these two galaxy populations are drawn from the same parent distribution, so you can't distinguish them. But if they have very low p-values, then this likelihood is very small. And so that means that these two galaxy populations are intrinsically different. And so we looked at, for example, at the galaxy sizes of these. So let's focus just on the orange points only of the cross-correlated halos, so only the halos that exist in both the dark matter and the warm dark matter simulation. So these are already the full multi-phase simulations, so not just dark matter. So they have the full physics in them. And we only focus on the orange points now, where we can see that for low mass halos, so this would be on the x-axis, the galaxies are different in warm dark matter compared to cold dark matter in relation to their galaxy sizes. But then for larger masses, they're indistinguishable. So this is kind of what is expected, because the impact of these different forms of dark matter would be expected to be most for lower masses. And this is something that we can already see quite clearly. And then the same, we can also look at the maximum rotation speed. So this is to look at properties that are also relatively easy to observe. And here we have the same, especially for isolated dwarf galaxies. So these are all halos, and then these split up between satellites and isolated galaxies. And then for isolated galaxies, it's clearer to see. While in satellite galaxies, it also depends on how much is stripped. So it's a bit washed out more. So now we see some properties that are very sensitive to the different types of dark matter. And we can look at that further, whether this is also the case, whether they are more or less sensitive than if we have different subgrid prescriptions, so to kind of disentangle the different components that go in that. And this is just kind of a sanity check, that if we just look at the mass distribution, then they're indistinguishable, so that the halo masses of this cross-correlated sample is by design is the same, but then still, even though the halo masses the halo mass distributions are the same, we still see differences in the galaxies themselves. So that is good, but it also means that this is also then sensitive to all the baryon physics, and not only to the cosmology. So this is kind of a broad overview on what is already in the literature and what would be the new contributions. So if we look at simulations with a single phase medium, so this would be the top row here. So this is where the ISM is modeled by this polytropic equation of state. We have, of course, on the left column would be cold dark matter. So there are a lot of simulation projects with a single phase medium and that use cold dark matter as the dark matter type. So for example, Eagle, but also TNG, Horizon AGN, Simba, and a lot of other projects. And then there are a few simulation projects that also use, that have full hydro, and then look at the warm dark matter variation of that. So this, for example, Mark Lovell has worked a lot on that. But then when we look at full cosmological boxes that are run until redshift 0 that use a multi-phase medium, there is only one that has come out just, I think, 2 weeks ago, 10 days ago, which is Firebox for cold dark matter, but there's nothing yet for warm dark matter. So this is kind of what we want to fill in to run simulations with a multi-phase medium with both cold dark matter and warm dark matter, so that we can really see which had the bigger impact. Where did we make the biggest improvement in terms of comparison with observations? Is it from going from cold dark matter to warm dark matter? Is it from going from a single phase medium to a multi-phase medium? Or do we need the combination of both of them to get closer to the observations? Good. Yes, so this is just to say that we will do the rotation curve of diversity analysis, but we need a slightly bigger box for that. So this is work in progress. And then this is already the last slide. This is what I said is still left. So we want to look at it from all angles, but this is something that is a new collaboration that I'm now starting. So Christoph has mentioned in the introduction that I will be working in Vienna from September on. And there I will be working with Glenn van der Ven and his group, who is doing a lot of dynamical modeling of galaxies to really see how our simulations can also help maybe to validate different observational techniques and to see whether there is also something that needs to be done from the observational side to make it easier to compare with simulations, in addition to all the efforts that we do from the simulation side to make them match the observations better. And this is also improved with the multi-phase ISM because more things are already directly modeled and we don't have to make assumptions after the fact on how different things are structured. So this is already my summary slide. I think I covered a lot of these points and I hope I convinced you that this is something very tricky, that if there is something that does not match directly between simulations and observations, that it might be easy to point a finger at one of these components, but I would probably bet that it is a combination of at least a few of them that will help to bring the simulations closer to the observations, or maybe even a little bit vice versa. So thank you very much for your attention, and I'm happy to answer any questions.
Yeah, thanks again, Sylvia, for this nice talk. And yeah, we are up for questions. Please raise your hand. Well, while people think about questions, I have one. So when you do this multi-phase medium, remove the equation of state, are there any drawbacks of these methods? Usually when you change something, you get one problem for another, usually a hopefully smaller problem, but still. Is there some hidden problem that you have already encountered there?
Oh yeah, a ton. Otherwise, we would have done this project a few years ago. So yes, typically that means that if you don't smooth out your gas with this artificial pressure, you get higher densities, which is computationally typically more expensive already as it is, because the time step goes down if you go to higher densities. But then also, for example, your feedback might become inefficient. So if you just dump your energy of a supernova explosion, just a thermal energy, into a very high density clamp, then all the energy will be radiated away on a very short time scale, and it will be just as if you had not done any supernova feedback at all. So this is why we needed to adjust things on a lot of different ways. So for example, also include the early feedback, and then not implement supernova completely thermal, but also with a kinetic component. So I would say that this is the drawback. The nice thing is that if it works, and we now have a model that works very nicely also for a large range in different mass resolutions, then I think there are no more drawbacks. But I think it's a lot more complicated to get it to work, because a lot of the processes that were just swallowed by these equations of state are now directly modeled. And as soon as you directly model something, it can of course go wrong in a lot of different ways if it's not done properly.
Thank you. Any more questions, maybe from some students or postdocs or anyone? Okay, if there is no question, I will ask another one. So when you mentioned this model with the different projected axes on it, so you have this simulated galaxy and you do measurements and get different rotation curves. Is this on the observational side? Huh?
Sorry, I think I lost you for a moment. I don't know whether that was on my end. Could you please repeat? Oh, I think it was on my end.
Yeah. So when you were showing this, so when you were showing this model of like a simulated galaxy and then with different projected axes to measure the rotation curve. Is this something which in observations could be solved by going more to IFU data? Because usually when you measure rotation curve, you do long slit spectroscopy. So you have one axis, but now with increasing amount of IFU data, is this something that can be also better tested in the observations?
Yes, so this is a very good question. It is true that IFU data help a lot, but even you also need to make assumptions on kind of this this different modes that are the non-circular motions or the thickness of your galaxy. So it helps some, but they have also shown that even with this, so even if you model, so this persists even if you model your galaxy with something like Barolo 3D, which is like one of these tilted ring models that that is one of the standard ways to analyze the kinematics of a galaxy, then that still persists. But yes, that's why yes. So this is one of the things that I'm very interested in collaborating with Glenn van der Ven and his group, because they do very detailed kinematic modeling and dynamical modeling, and then we will see if this problem is still there to the same extent as we thought it would be based on the simulations, or whether this is something that has been improved a lot.
Yeah, thanks again. So we have still time for questions. Any more questions? If there are no more questions, we can thank the speaker again for the talk and stop the recording.